Okay, so today we are going to solve some problems. So the first problem, suppose let an equal to summation k equal to 1 to n by n square plus k be a sequence. Okay, this is defined for all n in n. Now what can you say about the sequence an? Then the sequence an is, so first option is convergent. The sequence is convergent sequence, or bounded but not convergent, bounded but not convergent sequence, and then third option is diverges to infinity, and then the fourth option is neither bounded nor diverges, neither bounded nor diverges to infinity. Okay, now so we have to expand this summation. So therefore what is an? An is nothing but if substitute k equal to 1, we get n by n square plus 1, and then if substitute k equal to 2, we get n by n square plus 2, and so on. In the final term we get n by n square plus n, and we know that 1 by n square plus 1 is always less than 1 by n square, because 1 by n square is bigger than 1 by n square plus 1. Again, if we take 1 by n square plus 2 is also less than 1 by n square. Therefore this is strictly less than, the denominator is always less than 1 by n square. Therefore the first term we have n by less than n by n square, plus the second term is less than n by n square, and so on, the last term n by n square. So there are how many terms? There are n terms, therefore n square by n square we get 1. So therefore what you'll get, each an's are strictly less than 1 for all n in n. All the an's are less than 1. Therefore the sequence is bounded sequence. So therefore it's a bounded sequence. Therefore it cannot be diverges to infinity, because it is bounded. Therefore we cannot say this. Therefore we cannot say this. Now the next question is this converges or not? So if you mark all the, because all the an's are positive, because everything is a natural number, therefore an's are strictly greater than 0. Okay, and then lies between 0 and 1. Therefore 0 is here, 1 is here. So if you find a1, a2, etc., so all the an's are within this interval. Okay, it cannot converges to 0. Okay, so therefore, but is less than 1, therefore it's not convergent. Okay, you cannot say if you find a1, so what is a1? Substitute n equal to 1, you get 1 by 1 square plus 1, that is 1 by 2. What is a2? 2 by 2 square, 4 plus 1 plus 2 by 4 plus 2, that is a2. So that is nothing but, you can take 2 outside, 2 by 5 plus 2 by 6, that is your 11 by 30, that is 22 by 30. So 22 by 30 is actually 0. Anyway, it lies between 0 and 1. So this is 1 by 2, a1. What about a2? So the value is 0 point, or we can cancel it. Okay, we can cancel this 15, 11 by 15. So what is the relation between this 11 by 15 and 1 by 2? This is greater than this. Okay, because 22 is greater. Therefore, we get A2 is here. And if you find A3, you'll get somewhere. So therefore, it's increasing and bounded above by 1, but is strictly less than 1. Therefore, we cannot say AN converges to 0. Why? Because if AN converges to 1 means what? Sorry, AN converges to 1 means what? After certain stage, all the ANs are very close to 1, but all the ANs are strictly less than 1. Suppose if you take the midpoint of these numbers, if you take that epsilon, so if you take very small epsilon, there is no ANs in this neighborhood. Therefore, AN is not converges to 1. Okay, because strictly less than 1. We can choose epsilon very small, then in that neighborhood there is no AN. But these ANs are increasing. Therefore, this is bounded sequence but not converges. Okay. Therefore, convergence is false. Therefore, bounded but not converges. If you find A3 again, just you can find A3, you can just mark it the points. You will get very near to 1 but not converges to 1. Okay. So next problem. Using the Riemann integration, the value of, otherwise, okay, one more thing, the number of real roots, of the equation x cube plus x minus 1 equal to 0. So by Descartes' rule, we know that the number of changes is the number of positive roots. So here, how many changes? We have only one changes. Therefore, the maximum number of positive roots is less than 1 or less than or equal to 1. So number of positive real roots. Because real roots means either positive roots or negative roots. By Descartes' rule says the number of changes in f of x is at the most that many number of real roots, positive real roots. Here we have only one changes plus minus. Okay, so maximum we have only one real roots. What about negative? The number of negative real roots is the number of changes in f of minus x. So this is f of x. What is f of minus x? You just replace x by minus x, you get minus x cube minus n minus 1. There is no changes here. Okay, everything is minus. Therefore, should be less than or equal to 0. Therefore, should be 0. So therefore, and this is a first degree, this is a odd degree polynomial. So any odd degree polynomial have a real root. Therefore, it has exactly one real root. Okay, this is simple thing. Now, the next problem.
Sir.
Yeah.
Sir, how did you say that, sir?
Sorry.
How did you say that, sir? Like the positive number of positive roots.
Yeah, this is a theorem. This is a Descartes' rule says if you take given any polynomial f of x or any equation f of x equal to 0, okay, the number of positive real roots, number of positive real roots is bounded by the number is less than or equal to number of changes in f of x. That is, changes means what? Plus to minus or minus to plus. And number of negative real roots, the maximum number of negative real root is less than or equal to number of changes in f of minus x. Changes in the equation f of minus x. Now here f of x is nothing but this one. Here only one changes. Because this is plus, plus, minus. We have only one changes. Therefore, the maximum number of positive real roots is less than or equal to 1. But if you consider f of minus x, we get a minus, minus, minus. There is no changes. Therefore, the number of negative real roots bounded by 0. So the number of means is a positive number, therefore it should be 0. Therefore, there is no negative real roots. And here we know that the number of positive real roots maximum 1 may always 0. But this is a odd degree polynomial. So any odd degree polynomial have at least one real root. Therefore, definitely one positive real roots. Therefore, we have only one real root. Because there is no real root. There is no negative real roots. But it has a real root. Therefore, should be only one positive real roots by Descartes' rules. Okay, this is a theorem actually. Descartes' sign changes. Okay. So the next problem. Got it or not?
Yes, sir. Understood, sir.
So the value of the limit n goes to infinity summation k equal to 1 to n 1 by square root of n square plus k times n. So what is the value of this? Is first option is 2 into square root of 2 minus 1. Second option 2 into square root of 2 minus 1. Third option 2 minus square root of 2. Fourth option 1 by 2 times square root of 2 minus 1. So we have to write in of the form k by n. Okay, so already we know that. So we have to convert this into this format. So limit n goes to infinity 1 by n summation k equal to 1 to n f of k by n. We have to convert or rewrite this form. Now consider the given thing. So limit n goes to infinity summation k equal to 1 to n. You can take n square outside from the root. Therefore, we get n square root of 1 plus k by n, because n square is not there. Therefore, you have to multiply by divide by n square n cancel, we get n. Okay. Now this summation is depends on k. Therefore, you can take n outside. Therefore, limit n goes to infinity 1 by n summation 1 by square root of 1 plus k by n, where k equal to 1 to n. Therefore, this is nothing but integral 0 to 1 f of x. So what is f of x? You have to replace k by n by x. Therefore, we get 1 by square root of 1 plus x into dx. Now, what is the integration of this? So this is nothing but, so you can take 1 plus x power minus 1 by 2 integration 0 to 1 dx. So you'll get, can add power 1. Therefore, we get 1 plus x power plus 1 by 2 by 1 by 2. 0 to 1. So 1 by 2 is nothing but 2. 2 into, substitute upper limit 2. 1 plus 1 is 2, that is square root of 2. Minus lower limit 1. Therefore, 2 into square root of 2 minus 1. The first one is the correct answer. Okay. Now, the next problem. Okay. Fourth problem. Which of the following condition does not imply that which of the following conditions does not, is very important, does not ensure the convergence of the sequence? Of a real sequence an. So the first option is, suppose the an satisfy the condition modulus of an minus an plus 1 converges 0 as n goes to infinity. From this, can we conclude that the sequence an is convergent? The second option, suppose the series summation an minus an plus 1 is convergent, then from that can we conclude that an is convergent? And third one is suppose summation n into an is convergent. From this, can we say an is convergent? Then the last one is suppose the subsequence a to n plus 1 and a and then a 3n, the subsequence are convergent. Convergent subsequence. Okay, these are a subsequence. So from this, can we conclude an is convergent? Okay. So what is the thing? So clearly, the third one is now we cannot say from if this is true, then we cannot say an does not converges, because what is the question? Which of the following condition does not ensure that the sequence is convergent? But if you look at the third option, n into an is convergent series. So that means what? N into an converges to 0. Nth term always converges 0 if the series is converges. So converge 0 means what? That an, this is bounded by some constant, okay, epsilon. Okay. So that means what? An modulus of an is less than or equal to epsilon by n. And this is nothing but modulus of an minus 0 is less than or equal to epsilon by n. So therefore, an converges to 0. So if this is happened, then it's converges. But we don't want an is convergent. Therefore, this is not correct answer. Okay. Because already we know one theorem that if the relation satisfy the condition, suppose modulus of an minus a is some less than or equal to c times some bn, where bn converges to 0 and c is positive, then an converges to e. We know this result. Okay. So using this, from if 3 happens, then an always converges to 0. But we don't want an is convergent. Okay. Now, similarly, take the second case. Okay. And actually, I am missing one more sequence here. So a 2n minus 1. So all the even terms, odd terms, and then multiples of 3 are convergent subsequence. The original sequence is convergent. Okay. Therefore, last also not true. Similarly, we can work for B. Okay, suppose this is convergent sequence, this converges to the nth term converges to 0, otherwise the partial sum is bounded. Therefore, we can conclude that this is, from this we can say that an is convergent. But if the sequence is converges, the an minus an plus 1 is converges 0, from this we cannot say an is convergent. Why? If we take the counter example, an equal to square root of n, clearly this an is not convergent. It's divergent sequence. But this an satisfies the condition modulus of an minus an plus 1. What is this? It's nothing but square root of n minus square root of n plus 1. We can multiply and divide by the square root of n plus square root of n plus 1. We can, therefore, in the numerator we have 1 by square root of n plus square root of n plus 1. We can multiply and divide by the square root of n plus square root of n plus 1. The numerator we have a square minus b square. Therefore, we get a 1 in the numerator. So as n goes to infinity, this goes to 0. Therefore, this an satisfies the condition, but an is diverges. It's not converges. Okay. So therefore, from this does not ensure that the sequence is converges. But this is, if you take this, if you assume this, the series is convergent, then the sequence is convergent. Okay, because if you take the partial sum, you'll get an is bounded. Otherwise, we can say an is a Cauchy sequence, we can say. Therefore, every here in this case, a real case, therefore, every Cauchy sequence is convergent. Therefore, this is true. Okay. Now, next problem. Fifth problem. Suppose f is a function defined on open interval 1, 4 to R. Be a uniformly continuous function. Be a uniformly continuous function. Okay. And if we take some Cauchy sequence in this interval, so and let an be a Cauchy sequence. Be a Cauchy sequence in the interval 1, 4. Okay, 1, 2, not 4, 1, 2. Within this interval, 1, 2, we take some Cauchy sequence an. Again, now we define two sequence. Let xn equal to an square times f of an square, and another sequence yn is 1 by 1 plus an square into f of an square. This is defined for all n in n. Now, what can you say about the new sequence xn and yn? Okay, both x and y are Cauchy sequence, or one is Cauchy, another one is not Cauchy, all the possible combination. Okay, but we are talking about only the Cauchy property. So the first option is both the xn and yn is Cauchy. Xn and yn is Cauchy. That is the first option. Second option is xn is Cauchy, but yn is not Cauchy. And third option is xn is not Cauchy and yn is Cauchy, but yn is Cauchy. The last one is neither, both not Cauchy. Okay, or neither xn nor yn Cauchy. Okay, so it's given that fn is uniformly continuous function, and we know that every uniformly continuous function take Cauchy sequence into Cauchy sequence. Since it's given that an is Cauchy, so an is Cauchy, and we know that product of two Cauchy sequence is a Cauchy sequence. Therefore, since an is Cauchy, implies that an square is also Cauchy sequence. Because we can say this is always open. Why this is happen? So we can easily so all the ans are we are taking in the interval 1, 2. Okay. Therefore, all the ans are lies between 1 and 2. Therefore, an square is lies between 1 and 4. Therefore, an square also a sequence in the given interval 1, 4. That's why I am taking an is 1, 2, because the an square should be in 1, 4. If suppose you are taking an is 1, 4, the an square is 1, 16, but 1, 16 is not our domain. Our domain is 1, 4. That's why we take an in the given that an is in the Cauchy sequence in the interval 1, 2. Now this an square also Cauchy sequence. Why this an square is Cauchy? We can prove this an square minus am square is bounded by epsilon. Okay, so this is nothing but an plus am into an minus am, because this is a plus a square minus b square format. Therefore, a plus b into a minus b, and this we can write the am minus am into am plus am by the properties of modulus, and we can apply triangle inequality to these. We get less than or equal to modulus of an minus am, and this is modulus of an plus modulus of am. Okay, all the ans are positive. Okay, therefore this an is bounded by 2, this is bounded by 2, therefore 2 plus 2 is 4. Therefore we get 4 times an minus am. Since an is Cauchy, therefore this an minus an is less than epsilon, therefore you can choose epsilon by 4. Therefore we get less than epsilon. Okay, you can choose work for epsilon equal to epsilon dash or ticket epsilon by 4. So since an is Cauchy, therefore an minus am is less than epsilon for every epsilon. In particular, I am taking epsilon by 4. Therefore, this is substitute epsilon by 4, we get less than epsilon. Therefore, an square also Cauchy sequence. Now, we get an square is Cauchy, and given that f is uniformly continuous function, so every uniformly continuous function take Cauchy sequence to Cauchy sequence. Since f is uniformly continuous on the interval 1 comma 4, and this an square is Cauchy in the interval 1 comma 4, implies or then f of an square is Cauchy. Okay, so now look at the new sequence xn. Now we proved that already we know that an square is Cauchy sequence, and this also Cauchy sequence. Okay, now we are in the real case. Okay, any Cauchy sequence is converges, but not converges in this interval, but anyways converges in R. So every convergence sequence is a Cauchy sequence in R. So an square is a Cauchy sequence, and f of an square is also a Cauchy sequence. Both are convergent in R, and the product is also converges in R. Therefore, is convergent in R. Therefore, is Cauchy sequence R. Therefore, is a Cauchy sequence, because this actually this xn belongs to where? Is in R, because it's a range, because we are taking f of this one, right? Therefore, this entirely in R, not in the interval 1 comma 4. But anyway, an square is in 1 comma 4, but we are multiplying here f of an square. Therefore, it is in R. So therefore, is convergence sequence. Therefore, it's automatically Cauchy. Xn is a Cauchy sequence. Now look at yn. This f of an square is Cauchy sequence. Therefore, it's convergent. Then what about this 1 by 1 plus an square? And we know the bounded by this. So 1 by 1 plus an square is always bounded by 1 by an square, because we are adding 1 here, right? Therefore, this is smaller than this one. And this is less than or equal to 1 by an, because all the ans are greater than 1. Therefore, this is happened. Now, since an is convergent sequence, because an is a Cauchy sequence, therefore it's convergent sequence. Therefore, 1 by n is also convergent. Therefore, this also convergent. So we will get a this is a convergent sequence. This 1 by 1 plus an square is a convergent sequence. Therefore, it's a Cauchy sequence, because we are in the real case. Every convergent sequence is a Cauchy sequence. Every Cauchy sequence is a convergent sequence. Therefore, now we get this 1 by 1 plus an square is convergent sequence. This is a Cauchy sequence. Anyway, it's a convergent sequence. Product of two convergent sequence is a convergent sequence. Every convergent sequence is a Cauchy sequence in R. Therefore, both the xn and yn is Cauchy. That is the correct answer. Okay. So provide here f is uniformly continuous is very important. Otherwise, we don't know f of an square is convergent or not. Since this f guarantee that f of an square is a Cauchy sequence, therefore it's automatically convergence. Okay, that is very important thing. Now the next problem. Sixth problem. Okay, if you find the radius of convergence of this power series, the radius of convergence of the power series summation an is at power n, where n equal to 0 to infinity. Anyway, now what is this an? A naught is 1, and an is defined to be 3 power minus n times an minus 1. So these are ans. Now what is the radius of convergence? So how to find the radius of convergence? So you have to take this an modulus of an power 1 by n. That is, you can take that Cauchy-Adamant formula 1 by r equal to limit modulus of an power 1 by n. Okay. Now from this, what is the value of this limit. So again, you can rewrite this one. So what is a n minus 1 is nothing but 3 power of minus n minus 1 a n minus 2, right? Because this is some reconciliation. If substitute n equal to n minus 2, n minus 1, you will get this one. So therefore, if you substitute here, you'll get 3 power minus n already is there, but 3 power, a n minus 1 can be written as 3 power minus of n minus 1 times a n minus 2. Again, for a n minus 2, we can write 3 power minus of n minus 2 times a n minus 3. So, and so on, we can rewrite. So, finally, we can go, the last term is a naught, but we know that a naught is 1. So, therefore, in the previous term, a power minus 3 power minus n minus what? It should be 1 actually. Okay. Because the sum should be here n, here n minus 1. Sorry, this is minus n, this is n minus 1. If you sum, you'll get minus 1. Therefore, it should be minus 1. If you reduce this, you'll get 3 power minus 1 into a naught. But a naught is 1, therefore no need to write. So this is a. So therefore, what is the nth term? an is. So base are same, you can add the power. So you can take minus outside. Therefore, we get 1 plus 2 plus etc. plus n. Right? So this is nothing but 3 power minus n into n plus 1 by 2. Correct? So now we take modulus of a n power 1 by n. So therefore we get 3 power, this n cancel, we get minus a n plus 1 by 2 modulus. But anyway, you can take 1 by 3 power n plus 1 by 2. So anyway, this goes to where? This approaches to 0. Right? As n goes to infinity, is very near to 0. Therefore, 1 by r is 0. Therefore, what is r? R is infinity. So, radius of convergence is infinity. Okay. Now, next problem. Yeah, another similar problem. 7th problem. Suppose an is defined to be 1 by 3 power n if n is prime number. 1 by 4 power n if n is not prime. If n is not prime. And what is the radius of convergence of the series summation a n x power n? The radius of convergence of summation a n x power n. So the formula, again we have to use the formula, but there is also one more formula is there, almost everything same. 1 by r equal to limit n goes to infinity supremum of modulus of a n power 1 by n actually. Or you can take a n power 1 by n. This is another formula, supremum of a n plus 1 by n. So all the a n's are either 1 by 3 power n or 1 by 4 power n. These are a n's. If you take raise of 1 by n, we get 1 by 3, 1 by 4, right? Because raise the power 1 by 4. Now you take the supremum. So what is the supremum? The maximum thing is 1 by 3. So therefore 1 by r is nothing but 1 by 3. Therefore r equal to 3. So this is one more similar. Actually, this equivalent to limit a n power n. This is less than or equal to this. Okay. So that is, we know that all the a n's power 1 by n is less than or equal to supremum of all the a n's, because supremum is always bigger than this one, right? Therefore now take the limit both the side, limit of this. Okay, therefore anyway we find the bigger number. Okay. Therefore the radius of convergence is 3. So this is another important formula. Suppose you have to take the coefficient of the series and then you take the supremum of this an power 1 by n. Okay. Now the next problem. Again the tan, all the things there. Then so you should know the Taylor series expansion of sin x, cos x, e power x, log x, tan inverse of x. All the formula you should know. Okay. Because the problem they will ask tan inverse of n by 2, what is the radius of convergence, all the things. Okay. Okay, then yeah, the next problem. Eighth problem. Suppose we define two sequences. First we define a1 is 1, and in general an plus 1 is defined to be an plus minus 1 power n into 2 power n. Sorry, 2 power minus n. So this is new sequence an. Another sequence bn is defined to be an plus 1, sorry, 2 times an minus an plus 1 minus an divided by an. So this is for all n. Now we have two sequences an and bn. Now what can you say about this convergence of an and bn? Okay. So the first option is an converges to 0 and bn is Cauchy. Second option is an converges to a non-zero number. So a non-zero number I call some c, okay, but c is non-zero, and bn is Cauchy. Okay, the third option, an converges to 0 and bn is not Cauchy, not convergent sequence. Bn is not convergent. So the last option, an converges to a non-zero number, c a non-zero number, and an is not convergent. Sorry, bn is not convergent. Okay. Now, what can you say about this an? Is an is always convergent. So first list what is a, what is a1, what is a2. Already we know that a1 is 1. Now what is a2? If substitute n equal to 1, we get a1 minus, because minus 1 power 1 is 1, 2 power minus 1. So a1 is 1 minus 1 by 2. So therefore a2 is 1 minus 1 by 2. Now what is a3? a3 is nothing but a2, if n equal to, therefore plus 2 power minus 2. Already we know that a2 is 1 minus 1 by 2 plus 2 power minus 2 is nothing but 2 square. This is a3. So therefore directly we can write a4 is nothing but 1 minus 1 by 2 plus 1 by 2 square minus 1 by 2 cube. Okay. Therefore here 4 means we have a 3. Therefore in general, what is an is 1 minus 1 by 2 plus 1 by 2 square minus 1 by 2 power 3 plus and so on. So we can write minus 1 power n 1 by 2 power n minus 1. Okay. Or an plus 1 equal to this thing. Now, what is the value of this? If you sum this, simplify this, so this is okay, if we take minus 1. Because for odd powers we get a minus, for even power this one. Okay. So therefore we can write this geometry series. We can write 1 plus, that value is 1 by 2 plus minus 1 by 2 whole square plus and so on plus minus 1 by 2 power n minus 1. Okay. Now this is a geometry series about the point c equal to 1 by. Therefore, this is converges to 1 by 1 minus c, but 1 minus 1 by 2. So therefore, 1 by 1 plus 1 by 2 is nothing but 2 by 3. Therefore, an is converges to a non-zero number 2 by 3. Therefore, we can omit the last option and then first option, because they say an is converges 0. But an is converges to a non-zero number. Okay, therefore the last two option we can omit. Now we can talk about bn. Now what is bn? Bn is 2 times an. So therefore now substitute an plus 1 value here. Therefore bn equal to 2 times, what is an? An plus 1 is an plus minus 1 power n 2 power minus n minus an divided by an. Now multiply 2 inside, we have 2 an. Already we have 1 an, therefore we get just an. Plus, already we have 2, therefore minus 1 power n 2 into 2 power minus n whole divided by an. If we cancel an, we get first term, we get 1 plus 2 by an times minus 1 power n by 2 by n. We can anyway, you can cancel 1, 2, we can put 2 power n minus 1 anyway. So as n goes to infinity, this goes to where? Since the first term is constant term, therefore converges to 1. Plus this an is converges to 2 by 3, therefore 1 by n converges to 3 by 2. Anyway, this 1 by 2 power n converges to 0. Even this goes to some non-zero number, but this term goes to 0 because 1 by 2 power n, therefore converges 0, therefore this is 1. Therefore this an is convergent sequence. But the third option says bn is not convergent, therefore it's not convergent, it's not. Since it's convergent sequence, every convergent sequence is a Cauchy sequence in real case, therefore bn is Cauchy, therefore the second one is 2. Okay. Now the next problem. Suppose we have a function defined on open interval minus 1 to open 1 to r, defined by f of x equal to x square by 1 minus cos x. Okay. So for x non-zero, because for x equal to 0, 1 minus cos 0 is 1. 1 minus 1 is in the denominator, we get a 0. That's why for x non-zero, we define this one. For what about for x equal to 0? For x equal to 0, we define 2. So f of 0 value is 2. Okay, anyway. Now suppose if f of x write in the Taylor series expansion, summation a n x power n, if you write in the Taylor series expansion for all point x in the open interval 0, 1. Now the question is, what is the value of the sum of the the odd terms a n plus a 2n plus 1, where n equal to 0 to infinity. So what is the value of this odd term sum? So the first option is 0. So the second option is 1 by 2. The third option is 1. The fourth option is 2. So now just write what is f of x. So it is given that f of x can be written as in the Taylor series expansion, summation a n x power n. But what is f of x? X square by 1 minus cos x equal to, if you substitute this thing, we get a naught plus a1x plus a2x square and so on. Okay. Now for the point, if substitute x equal to 1, what will get? In the right hand side, we get 1 by 1 minus cos 1 equal to, so what will get? A naught plus a1 plus a2 plus and so on. Because substitute x equal to 1, you will get this one. Now if substitute x equal to minus 1, therefore minus 1 square is again 1 by 1 minus cos of minus 1 again cos 1. Because cos is an even function. Cos of minus x, so minus 1 is cos 1. So, but here we have alternative plus and minus. A0 minus A1 plus A2 minus A3 and so on, plus A4 and so on. But we need a odd terms. So we have to subtract, maybe we call this equation number 1 and this is equation number 2. Now subtract 1 and 2, the left hand side we get the same number, therefore 0. If you subtract with the left hand side, we get 0. The right hand side we have all, so this minus A0 cancel, A2 cancel, we get only the odd terms. Therefore summation 2 times, because we get 2 times the odd terms. But we can cancel 2, because if we multiply by 2, we get, multiply by 1 by 2, we get this one. Therefore the answer is 0. Okay. Now the next problem. Yeah, for uniformly continuous, it's very important thing. 10th question. Which of the following is uniformly continuous? So I forgot to mention one result. So maybe state the result. So suppose f is a function defined on some interval I to r, okay, and it is differentiable, and its derivative, the modulus of f dash of x, is bounded by some number. That is, the derivative is bounded on the interval for all x in the interval I, then f is uniformly continuous. F is uniformly continuous on the interval I. Suppose f defined on the interval I and the derivative is bounded, then the function is uniformly continuous. So one more important result. Now, next question is, which of the following functions is uniformly continuous? Respective domain. Which of the following functions is uniformly continuous on the domain stated? So the first function, f of x equal to x square, okay, the domain is entire R. The second function is f of x equal to 1 by x, where x varies in close to 1 comma infinity, open infinity. The third function, f of x equal to tan x, where x in the interval minus pi by 2 comma pi by 2 is uniformly continuous or not. So the last one is integer part of x, f of x equal to integer part of x, where x varies in the closed interval 0 comma close to 1. Okay. Now look at the first option. Actually, f of x equal to x square is continuous function, but not uniformly in the entire R. Okay, because we cannot we cannot get this f of x minus f of y is strictly less than epsilon. But this is nothing but modulus of x square minus y square. But you'll get a mod x minus y into mod x plus y. You can choose delta by epsilon by x plus y. Therefore, this epsilon depends on x and y. Therefore, it's continuous but not uniformly continuous. But if suppose this x varies some interval, then we can bound this x plus y by some number. Then we will get delta. We can choose delta depends on only epsilon. Okay. Therefore, this is not uniformly continuous. Otherwise, we can prove some other way. We know that some theorem, if x and f is uniformly continuous And if you take any sequence xn and yn with xn minus yn is converges to 0, then f of xn minus f of yn also converges to 0. We know this result, provided f is uniformly continuous. If you take any sequence x and yn, but we don't know about x and yn converges or not, but the subtraction converges to 0, then this f of xn minus f of yn also converges to 0. We can produce some x and yn, but the subtraction converges to 0, but this f of xn minus f of yn is not converges to 0. So can anyone give that thing? So if we take if you take xn equal to something and yn equal to something, but xn minus yn converges to a thing. Suppose I'm taking n and this is n plus 1 by n something. Now if you subtract n and cancel, we get 1 by n, a modulus of anyway, we're taking modulus anyway, so not an issue. So otherwise take minus 1 by n, it's not an issue. So therefore this x and yn satisfy this condition. What is f of xn is n square minus this is actually f of yn square is nothing but 1 minus n whole square. Okay, this is f of n, this is f of xn, this is f of yn. So if you substitute this, you can n square minus a square, that is n square plus 2ab plus b square anyway. So if you multiply this, we can cancel all the things. Is converges to minus 2, right? Because n square cancel, this n cancel, this 1 by n square anyway 0. We get 0. We converge, is converges to 2. Anyway, it's not converges to 0. But what the theorem says, if f is uniformly continuous, and if you take any sequence x and yn, and xn minus yn converges to 0, then f of xn minus f of yn is also converges to 0. But if you take this particular sequence x and yn, this xn minus yn converges to 0, but f of xn minus f of yn not converges to 0. Therefore, the first one is not uniformly continuous on the interval. Now look at the second one. We can easily find the bound for this one. Anyway, so since all the x are bigger than or equal to 1, because x varies in this interval, so therefore 1 by x is less than or equal to 1. Okay, so you can take f of x minus f of y modulus is 1 by x minus 1 by y. If you simplify, if you take modulus outside, we get a modulus of x minus y by xy. But x less than y, 1 by x less than y, 1 by y less than y. Therefore, this product also less than y. Therefore, this is less than or equal to just mod x minus y. Therefore, choose delta equal to epsilon. You'll get thing. Otherwise, since this is a differential function, what is f dash of x? So f dash of x is nothing but minus 1 by x square. So if you take modulus of this, so it's bounded by 1. So since the derivative is bounded, therefore f is uniformly continuous in the interval 1 to infinity. Okay, either you can use definition or use the theorem. Okay, therefore this function is uniformly continuous. Now look at the third one, f of x equal to tan x in the interval open interval minus pi by 2 plus pi by 2. Suppose if the function is defined on closed interval, then this is uniformly continuous. So now we are going to think about, can we extend this function to these endpoints, minus pi by 2 or plus pi by 2? No, because we know that tan pi by 2 is infinity. So this function we are not extend to these endpoints, either these endpoints or these endpoints. Okay. Therefore, this is continuous but not uniformly continuous. Otherwise, again, you can give the example of 2 x and yn. Xn minus yn is converges to 0, but f of xn minus f of n not converges to 0. Otherwise, we can easily say that this function cannot extend to these endpoints. Therefore, this is not uniformly continuous. Now look at the last one. So look, if you draw the graph, you can easily answer this question. First of all, you have to check this is a continuous function or not. So this is 0 and this is 1. So what is the integer part of 0 is 0. And what is the integer part of 0.5? Everything 0. So what do you mean by this integer part of x is an integer which is less than or equal to the given number x. So if you take 0.9, what is the integer part of 0.9? Is nothing but 0. Only take the integer part. So, but what is the integer part of 1 is 1. So therefore the graph is up to this you get 0, but for 1 it goes to 1. So therefore, even the function is not continuous at the point x equal to 1. Because at x equal to 1 it jumps to 1. But all other values take 0. For x equal to 1, integer part of 1 is 1. Okay, so this point is 1. So therefore, this function not continuous at a point x equal to 1. Okay, therefore we cannot talk about uniformly continuous. So uniformly continuous, first of all, should be continuous. Okay, so therefore the last one is not even is continuous. Therefore, it's not uniformly continuous. Okay. Okay, maybe there are so many similar problems are there. Okay, so I state one important result. So you say, suppose there are numbers a1, a2, etc. some ak, all are positive, greater than or equal to 0, real numbers. Then what is the limit n goes to infinity a1 power n plus a2 power n plus etc. plus an power n whole power 1 by n. What is the value? So the question maybe they ask like that, what is the limit n goes to infinity 2 power n, 3 power n, 5 power n, whole power 1 by n. What is the value of this sequence? This is nth term. New sequence a2n power this one. So I already mentioned in my notes. So this is nothing but maximum of a1 to ak. So maximum of all this number a1, a2, etc. ak. Okay. So we can easily prove that one. So therefore, using this formula, so therefore, what is the value of this? Maximum of 2, 3, 5. Therefore, this is nothing but just 5. So therefore, the limit of this sequence 2 power n, 3 power n, 5 power n, whole power n is converges to 5. So this result is very important. So provided all the an's are positive. Okay. So we can find this formula in my notes. So it's nothing but maximum of this thing. Okay. So almost we solved all the problems. So just to go through that book, my book already shared to you. You can find more problems, and then you can try to solve it. If you have any doubt, you can ask me. Okay. Now you stop the class.